Okay, so we've started the recording. It might have been wise to record the introductions, but that's totally fine. I'll turn my video back on for a second here. There we go. Just so the recording picks up the tweed jacket that I bought just for today. Anyway, yeah, so we're going to do a PowerPoint presentation today. That's going to be most of what we do, just introducing the course and myself as an instructor, and then we'll have time for an exercise at the end. I don't think we'll use the full hour and a half, but we'll see. But we'll definitely take a break in there somewhere because it's a night class and an hour and a half is a long time. So hope everybody's comfortable. We'll jump right into it. So I'm going to share my screen. I'm probably just going to share the whole dang screen here. The whole screen. Yep. Okay. And we're going to get started on my PowerPoint presentation. So really quick, I'm going to start the show here. Can I just get some verbal confirmation from somebody that you can see the PowerPoint that's on the screen here?
You see it?
You got it? Okay, good. I made a custom PowerPoint template just for this. So this is also the only time that you're going to see like Paul McKee, PhD. I don't plan on being Dr. Paul or Professor Paul or anything like that during the semester. I'm just going to be regular old Paul. I thought about that. I mean, partially it's like, oh, you know, I could go on an eco trip and make people call me Dr. Paul. And there's reasons why. Like, I think it's appropriate to call your professor, you know, Dr. So-and-so or Professor so-and-so. But I spend the bulk of my time every week at NASA. And at NASA, we've got an army of PhDs, and nobody is Dr. anything. It's very like King Arthur and the Knights of the Round Table. And so, kind of following off of that culture, I'm going to ask Gil to call me Paul if you're comfortable with that. Yeah, we'll get into the lecture one presentation here. So we'll start with me, my story. So right now, I'm not local to New York at all. Right now, I live in Houston, Texas. But I grew up in New York State in Rensselaer County in a small town called Averill Park, which is right here next to the red arrow, where Troy, New York, and specifically RPI is the gray arrow. So I grew up kind of in the shadow of RPI. And I knew from a relatively young age that I wanted to be an engineer, and I knew that I wanted to go to RPI. I did not necessarily want to go to RPI for 10 years, but that is ultimately how it worked out. So I graduated Averill Park High School, class of 2013, and I knew that I wanted to go into engineering. However, RPI is rather expensive, and my parents kind of voluntold me to save a little bit of money and get an Associate of Science degree first at a local community college called Hudson Valley. Some of you might have heard of that place. Hudson Valley is just down the road. It's in kind of the southernmost portion of Troy. Got an Associate of Science in Engineering Science, kind of got my first 2 years of schooling out of the way. And I transferred to RPI, and I didn't know what my major was going to be. And I knew that I wanted to do something with space, but that was kind of it. Like space and robots were both pretty cool. And so I thought, well, mechanical engineering affords me the most flexibility as a major. It kind of gives me the most chance to pick and choose classes. And I took a class called Modeling and Control of Dynamic Systems, or ModCon. And those of you that have taken that class might have seen something like this, a rotary inverted pendulum, where there's a motor kind of at the base here. And we did a demonstration. So Dr. Hurst was the professor that semester. That would have been the fall of 2015. He was the professor, and he showed us this rotary inverted pendulum where a motor here at the kind of shoulder is able to keep the wrist and forearm linkage here vertical, even if you kind of poke it and prod it and try to perturb it a little bit. It does a really fantastic job of balancing the pendulum. And I was so mesmerized by this. I thought it was the coolest thing ever. And I thought, my gosh, that's it. I want to do that. Whatever it is that I need to learn to do that sort of robotic, cool, dynamic system, embedded control, whatever it is, you know, that sort of robotics, I want to do that. And I can actually trace a direct thread from that first semester of ModCon to my job at NASA now as a guidance, navigation, and control engineer. Essentially just taking classes that followed that, you know, what's after ModCon, mechatronics, and oh, I want to take space classes. And I met Kurt Anderson, who I'm sure some of you know, and I took his space vehicle design class, and I got my first internship at NASA, and kind of the rest is history. But I thought I'd mention that I definitely wouldn't be where I am today if it weren't for Dr. Hurst and certainly several other people at RPI, Dr. Anderson included, and that first ModCon lecture. So I get kind of nostalgic for that. Then I stuck around. So grad school is a terrible idea, and anybody here who's in grad school should rethink it. I decided to stick around for the co-term program and get a master's degree with Kurt Anderson, the space professor. At the time, he was the only space professor at RPI. And I did my research on dynamics and controls, and specifically dynamics and control of a CubeSat. So kind of the mechatronics sort of thing, maintaining the pointing accuracy of a spacecraft kind of under various perturbing conditions. And I said, I did an internship at NASA Goddard, and people they said, if you have any gas in the tank and you think you want to get a PhD, you should just do it. Just get it out of the way. Do it while you're young. Do it before you get married and have kids. And so I stuck around for a PhD, and I was going to do it with Kurt Anderson, but he said, well, it would be wise if you branched out, and also I don't think I'm really going to have the funding to do justice to you as a graduate student. There's a new professor who just moved in down the hall. His name is John Christian, and he introduced me to John Christian, and I signed on to his lab. So I spent 4.5 years as a John Christian PhD student. And of course, he's since moved on. John Christian teaches at Georgia Tech now, but he was my PhD advisor, and I did my PhD in autonomous optical navigation, which sounds a little bit different than CubeSat attitude dynamics and control, but actually they both fall under the broader umbrella of spacecraft guidance, navigation, and control, or GNC, which we'll talk about that today. And I actually got the chance, because I'm at NASA now, I got the chance to tag up with my mentor from like 2017, 2018, who convinced me to get a PhD. His name is also Paul. And I caught up with him at NASA, and I'm like, hey, Paul, that was awful. Getting a PhD was terrible. Why did you make me do that? And he said, ha, sucker. So to think that that was a half a decade of my life. Yeah, no. So anyway, those of you, I think pretty much all of you are graduate students. I joke about it, but I do think that there is tremendous merit to graduate studies, master's as well as PhD. So I'm very happy that you all are here, because I think with very few exceptions, it's tough to get into this class if you're an undergrad. But anyway, that's a bit about my story. I was a TA, so I think many of you know me as your TA. So I was a TA for mechatronics in 2018, spaceflight mechanics, space vehicle design, ModCon 3 times, spaceflight mechanics again in 2022. For the record, you're only supposed to be a TA at RPI 2 to a maximum of 4 times. And I did 7. And under normal circumstances, they would give me the boot and say, stop being a TA. But I really, really loved it. I absolutely adored being a TA. It turned out that a lot of the days I felt like I was slogging through the research so I could get to the TA work, which is completely backwards. It's usually the other way around. TA is kind of a necessary evil that you do just to get your paycheck, and then you go off and do the research that helps you graduate. But I fell in love with it. I love being a TA, love being a teacher, to the point that now I'm coming back as an adjunct professor, and I don't have to be here, but I want to. Like this is fun for me. This is dessert for me. There's a picture of me on the right. In 2019, I was awarded the TA of the Year award in the main department. My very first time that I was a TA, and I got a stack of nominations after that. But they don't let one person win more than once. So unfortunately, I just have to be happy with my stack of nominations. But this is kind of my teaching pedigree. So it's why those of you that don't know me already might consider taking me seriously. Maybe, maybe not. And then this is more recent history. So I finally graduated RPI in 2022. There's a picture of me there with Kurt Anderson, my master's advisor, at the doctoral hooding ceremony. I've moved to Houston, Texas, which is where I'm from now. Actually, I'm just a couple of miles away from the house where Neil Armstrong lived during the space race. And I've got a lot of cool NASA stories. I love talking about Houston. We could very easily go off on some tangents talking about the cool stuff that's going on at Johnson Space Center. I work there now in the Aeroscience and Flight Mechanics Division, which does guidance, navigation, and control systems. Most of my work is on the Orion spacecraft, but also a little bit of work on some lunar surface exploration. We'll talk about that, like the Viper rover and the Lunar Terrain Vehicle. I should mention, just to be clear, that this class is not a NASA class. This is something that Paul McKee put together on his own time, and with a little bit of time at work, because you're allowed to spend a little bit of your time at NASA doing research and stuff like this. But anyway, this is a me thing. So this is not a NASA affiliated or NASA approved course. So kind of buyer beware. There's your disclaimer. So I hope that y'all are still willing to stick around anyway, but I don't want you to think that you're somehow NASA certified, but you are Paul certified if you do well in this class. So hopefully that's almost as good. Anyway, that's me. So I want to just highlight a few of the people that made this class happen. So like I said, this class existed as a daydream of mine for a long time. Probably the most credit out of any single person goes to Kurt Anderson. He really spearheaded this. He wanted it to happen. I said to him that I wanted to be an adjunct professor, a remote adjunct professor, which did not exist at the time. Him and the main department head, Antoinette Maniotti, spoke about this, and they decided, them with other folks at RPI created a position, a job that does not exist, which is remote adjunct professor at RPI, and they spearheaded to really make this happen. I would have been happy teaching space vehicle design or spaceflight mechanics and kind of taking the pressure off of some of the more senior professors. But Kurt said, no, no, you're gonna teach navigation. And I said, Kurt, I really don't think I'm qualified to teach that. There's so many smarter people out there that could do it. People on the on the screen that you could see are so much more qualified than me to teach this course. And he said, that may be, but they're not here right now. And so either you teach it or it doesn't happen. And he basically just kicked me in the pants and made me teach this class. So huge thumbs up to Kurt Anderson, but also Antoinette Maniatti and Tom Haley in the main department really made this happen. Also, Dr. John Christian on the top right there, he was my PhD advisor. He taught a class called Main 6962. Might have been Main 6960. I should check that. You can probably find it in the course catalog. But he taught basically a very similar course in the spring of 2018, which was easily the single most useful class I've ever taken in my life. It was extremely useful. I learned a lot. And I use things from that class. Like I have my course notes from that class and I open them on a daily basis at NASA just to make sure that I'm doing things right. And so this class is based heavily on that class. And I'm really sincerely hoping that for some of you, this could be the same. This could be the class that kind of nudges your career in a certain direction or something like that. But even if this is just something fun that you take because you need credits, I certainly hope you enjoy it. But once RPI was on board, I still needed to get NASA on board because I'm a federal civil servant and I can't take a part-time job without like a stack of signatures. So a lot of credit to my immediate supervisors who I couldn't find photos of very easily. Tim and Jack are my immediate bosses at work, and they thought this was a great idea, and they gave me permission to work on this on my own time and a little tiny bit of work time as long as appropriate. Dr. Chris D'Souza is one of the smartest people I've ever met. He was on my PhD advisor's PhD committee, and he's also one of my coworkers at NASA now, and he kind of gave his blessing to this class. Then I needed approval from the head of the entire division at NASA. His name is Carlos, the GNC division, and he thought it was a great idea. And then I needed permission from the head of engineering for all of Johnson Space Center. Her name is Julie Kramer White, and she also thought it was a great idea. And if any of these people had said no, this class would not have happened. So I really feel like it's worth, saying thank you to all the folks at the RPI, onboarding and HR department, Johnson Space Center, the JSC legal department, my professors, my advisor. The list goes on and on. But anyway, I wanted to thank those people. And so how is this class going to work? So I alluded to this before, but I work full-time, 40 to 50 hours a week at NASA. This is a part-time gig for me. This is kind of a side hustle. My available time to commit to this class is lecture, which is going to be 3 to 4 hours a week, office hours, which is Wednesday, 2 hours per week, sometime on the weekends, and then intermittent time on nights if there's like a fire to put out, maybe, but no promises. So my bandwidth is going to be extremely limited. I'm going to do my very best, but y'all are going to definitely need to be self-starters. I highly recommend that you work in groups. If you have a problem and you can't figure it out, you can certainly email me at my RPI email, but I can only really promise to check that when I get home from work every day. And so this is definitely going to be something where I do my best to help, but because I'm an adjunct professor, this is going to take more than the normal amount of kind of dedication from you to make this work. So hope we can do that. So ethical disclaimer. At least a third, and actually I think it's more like 2/3 of this class were former students of mine. And at least a third of this class knows my personal cell phone number or knows how to contact me on Discord or knows my Steam account, or they know how to get in touch with me through other means. And they're people that I would consider my friends. And that's a big ethical problem. I mean, obviously that's a huge conflict of interest. And so how are we going to get away with this? How are we going to not get away with it? How are we going to circumvent the possibility of this being a problem? I don't want to give anybody preferential treatment. I don't want it to even look like I'm giving anybody preferential treatment. So 2 promises. There's 2 of them. The first one is completely anonymous grading. So for all of your homework assignments, except for the first one, and you'll see why, I don't want you to write your name on them. I want it to be just your RIN, your RPI identification number. And LMS has a procedure where I can go through and kind of hide names so it doesn't show me whose is whose. And I want to be as impartial as possible when I'm grading your assignments. The second one is everybody that can contact me through methods other than my RPI email, you are on your honor not to. If you text me or you reach out to me any other way, I'm going to have to smack you on the wrist and then ultimately give you a grade penalty. And I, people here are very honorable, and I trust you not to abuse that. But everybody here that doesn't have that privilege to just send me a text message, you can rest assured, we're all going to be grown-ups about this, and we're not going to have any preferential treatment. So that is my pinky promise to all of you. So what is this class all about? So I think moving forward, the next bunch of slides are going to be, we'll take a look at that in a minute. The next bunch of slides are going to be regarding like the content of the course and the way things are run. This is kind of a good natural pausing point. Does anybody have any questions or feedback? Or if there's anything in the chat, I'm afraid I can't read it, so somebody will have to tie in with their microphone. Nope. Otherwise.
I have a quick question.
Yeah, I got an answer.
Could you maybe make a WebEx team space so that we could make study groups easier?
Oh, sure. That would actually be a good idea. So I'll create a WebEx Teams for the class. And I can't promise that I will be an active member of that. But I think that would be good for y'all to get in touch with one another. Yes, I highly recommend. If anybody is soloing this class, you are doing it wrong. So please make sure that you have at least a study buddy, if not a group of people that you're working with. And yeah, definitely, like the more the merrier. Absolutely. Okay, thank you for that. Any other thoughts or feedback, or we're gonna start talking about navigation here?
I just wanted to say I have to go to another class at 7. I just wanted to make you aware of that.
Okay, well, thank you, Merritt. And I'm going to be recording all of my lectures and posting them as soon as I can on LMS. You might notice that LMS looks a little bit sparse right now, and that is because I just got access to it 2 hours ago, and I haven't had a chance to do anything. But yeah, so appreciate you making an appearance, and I certainly won't be upset if you have to drop off, and you should be able to get caught up from the video. All right. Anybody else? Good stuff. All right, and we'll have other opportunities to break for questions. So this class is about navigation. And so I mentioned before, GNC or GNC is kind of a subset of spacecraft engineering. Stands for guidance, navigation, and control. Maybe it should be navigation, guidance, and control. So it's 3 related problems. Navigation is determining a vehicle's state, and we usually mean its position, its velocity, or its attitude, otherwise known as orientation, or other parameters of interest. So you're basically estimating things. Navigation is an estimation problem, right? And that's what we're going to be doing this semester. We're not going to spend very much time on the others. Guidance is determining a path or trajectory from a current state to a desired future state. So it's like a boundary value problem almost. You've got your current position, velocity, attitude. You've got some future position, velocity, attitude. How do we make that happen? And finding the path is guidance. Actually doing it is called control. So that's manipulation of the forces acting on a vehicle through the use of various actuators to move a vehicle along the trajectory described by guidance while maintaining stability. So it's kind of a mouthful, but navigation is where am I? Guidance is how do I get to where I'm going? And control is actually getting to where you're going. So navigation is determining position, guidance is determining trajectory, control is firing thrusters. That's the way we can think about it. And you can see how these are all related to one another. And there are certainly many, many other classes at RPI. At one point I had a slide mentioning like other related classes that you should consider. But there are many other classes at RPI that would also be good if you felt like going into guidance, navigation, and control. Most notably, any class that has control in the name. Systems analysis techniques, which doesn't, but that's a great controls class. Optimal control theory is basically all of guidance is pretty much predicated on optimal control theory. There's a class called advanced calculus, which is basically calculus of variations. You should consider that. Certainly design optimization. I use that sort of thing all the time. I think Dr. Hicken teaches that class still. Mechatronics, any of the robotics classes taught by Dr. John Wen or any of his graduate students, those would all be great if you wanted to go into a career like this. And I've spoken with students. I was speaking to a student last week, actually, who was dead set on being a robotics engineer. And I was kind of trying to nudge him like, well, robots need to see, and vision-based navigation is kind of my thing. You should think about moving over into my division. Anyway, definitely consider that this is robot adjacent. So if you fancy yourself a robotics engineer, you'll definitely be able to learn a thing or two from this class. Anyway, these are the things we're going to be talking about in this class. So in order, roughly, it's going to be a review of orbital mechanics. So spaceflight mechanics or equivalent is a prerequisite for this course. If you haven't taken that, it's going to get pretty spicy pretty quick. I'm going to do my best to review all of main 4100 spaceflight mechanics in 3 hours, and that's going to be one of the first things that we do just to get that over with. So that people are comfortable with things like, classical orbit elements and transforming from one attitude frame to another and stuff like that. That's definitely going to be foundational, as well as IOD, which stands for Initial Orbit Determination, which is something that we do talk about in spaceflight mechanics, but I feel like there's not enough emphasis. So we'll talk about methods of using position or velocity or bearing measurements over time to determine the orbit of a spacecraft, which is a navigation problem ultimately. You're trying to find its full state, position, and velocity, which is the same thing as knowing all of its orbit elements. Anyway, I digress. We're going to talk about some foundational estimation theory. If you're familiar with least squares, we're going to be using plenty of least squares in this class. We're going to be talking about where least squares comes from and why it's actually the right answer to a lot of AX equals B type problems. We'll also be talking about maximum likelihood estimation, talking about covariance and uncertainty modeling and all that. Space to Earth and Earth to space navigation. I might as well write triangulation and trilateration. Those are kind of two methods of determining the position of a vehicle. Either if you're taking measurements from space, so think of GPS, you've got a signal from space being seen on the ground, or if you're taking measurements on the ground, maybe like a line of sight measurements to a passing spacecraft, and you're trying to triangulate its position. A lot of people say triangulate when they mean trilaterate. We'll get to that. But anyway, that's going to come up. Inertial navigation, which is navigation using accelerometers and gyroscopes. Essentially, it's kind of akin to, if you use a human body metaphor, it's like your inner ear is basically an inertial measurement unit, and spacecraft use those all the time. So we'll talk about that. One of the biggest units in this class is going to be spacecraft attitude determination using star trackers. And by the end of the semester, you will have coded up your own star tracker completely from scratch. We're also going to go into sequential state estimation. In other words, Kalman filtering. We'll talk about Kalman filters, extended Kalman filters, multiplicative extended Kalman filters. And then at the end, as time permits, we're going to talk about modern image-based navigation techniques, things like horizon-based optical navigation and terrain relative navigation and hazard detection and avoidance and all that. Also, I'm going to see what I can do to put together some guest lectures. So I have some coworkers at NASA that really want to talk about the stuff that they do, and if I could put together a guest lecture, that would just be peachy. So we'll see if we can make that happen. That would be towards the end of the semester. I should mention, by the way, we're into reviewing the course syllabus. So the syllabus I hopefully emailed out to everybody. If you don't have it up in front of you, we're basically going over it now in the slides. I'm going to post that on LMS pretty much as soon as lecture's over, so you'll be able to take a look at that. But we're basically kind of crawling our way through the syllabus now. Now, this is definitely not in the syllabus. This is my depiction of the entire course. So everything that we're going to learn in this semester is somewhere in this picture that I made. This is kind of a teaching philosophy of mine. I feel like professors have a bird's eye view of the entire course and they understand why every lecture is important. But when I was a student, I would often find myself thinking, gosh, why does lecture 7 matter in like a cosmic sense? And so what I want to be able to do is point back to this diagram every day or every lecture and say, well, here's what we're doing today. And so what I tried to depict is the Artemis spacecraft on a trajectory from the Earth to the Moon. My trajectory could use a little bit of love. That was the best I could do in PowerPoint art. But the trajectory represents orbital mechanics. So we're going to spend some time talking about the orbital mechanics that surround kind of the physics that's kind of the backbone of a lot of what we're going to be doing. You'll notice that the Earth is resting on top of a turtle, which is how it does in real life. And we all know that beneath the turtle is another turtle and that it's just turtles all the way down. That is a specific reference. So that's a joke. The Earth is not sitting on a turtle, and it's also not flat. And then beneath all the turtles is an abacus, which is meant to represent mathematics. So mathematics is truly going to be the foundation of everything we do here. And estimation theory is going to be a little bit boring when we first learn it, but you're going to find that we need it for everything we do afterwards. The magenta lines from the Earth to the spacecraft kind of represent triangulation and trilateration. So that's either navigation on Earth using space measurements or navigation in space using Earth measurements, the deep space network, that sort of thing. On board the spacecraft, you've got a gyroscope, which represents inertial navigation, and you've also got a computer that's not meant to be a robot's face. That's meant to be my kind of PowerPoint art of the Apollo guidance computer, and that represents Kalman filtering and kind of the math that a spacecraft needs to be doing at all times to make sure that it keeps track of its state. It's also seen taking a picture of stars, so we're definitely going to be talking about star trackers and star-based attitude determination, as well as taking a photo of the moon itself as it approaches, and that is for optical navigation and terrain relative navigation. So everything that we cover in this course is somewhere in this picture, and this PowerPoint is going to be posted, so don't feel the need to kind of do your best rendering of it. You can certainly take a look at it later. But I'm going to move on from this unless anybody has any specific questions. Otherwise, we can keep going.
This is a nit. Can you click hide on the Rensselaer.webex.com is sharing your screen?
I
Pop
thought
up.
that was all right. I feel dumb.
Thank you.
Thanks for saying something, Renee.
Sharing, it's like only on your screen. So sorry about that. Any other questions? Doing good? All right, we're gonna keep moving. So homework. There are going to be 7 graded homework assignments in this course, and each of them is worth a letter grade in the course. So take the homework very seriously. These are going to be challenging homework assignments. And so I would say those of you that have taken Kurt Anderson's spaceflight mechanics course, every homework assignment that I give is going to be roughly as difficult as one of the computational assignments that he gave. And as a matter of fact, my first homework assignment, I guess technically the second homework assignment, is based on one of the harder computational homework assignments that John Christian gave, and then I made it even harder. So the homework is going to be pretty rough, and I apologize in advance for that, but I think it's really going to be good. My kind of teaching philosophy, and this is what I've found from both teaching and being a student for 10 years at RPI, between the undergrad, bachelor's, master's, PhD. People don't remember what they see. People don't remember what they hear. People don't remember what they read. People don't even really remember what they study. They remember what they do. That's really what people remember. And so you are going to do a lot of very hard stuff in this class. There's going to be some very challenging open-ended homework assignments, which are going to really make you scratch your head. And there might be a few late nights, and I apologize in advance for that. But I really think that that's going to be what's best for your education. And so I'll certainly do my best to help on those. But warning in advance, the homeworks are going to be brutal. There are 7 of them. They're each worth an entire letter grade. Do not skip them. They are important. They're going to be due every other Friday at the close of business. So that's going to be 4:59 Eastern Time, submitted by LMS. I'm not extremely strict about the deadline, but you should really do your best. It would make me sad to think that you were staying up late on a Friday night working on this. I kind of want you to finish the assignment and then be able to take a weekend to relax and recharge. That's kind of how I was hoping this would work out. And then also that same weekend is going to be when I grade it. So, if you have a specific problem and you need a deadline extension, we can absolutely talk about that. I'm going to be reasonable. But in general, it's going to be due every other Friday at 4:59 Eastern Time. I can't guarantee. So I put this in there as I fully intend to accept late work and to not be too mean about it, but I have to put on the syllabus, it's like a CYOA thing, right? It's like, all right, I do reserve the right to inflict a grade penalty if you are late, especially if you're egregiously late and you don't talk to me about it. That's really what would upset me. If you let me know that something is going on in your life, if you're going to a conference or if you need to travel or something like that and you need an extra day or two, or if you're just having a mental health crisis, which absolutely happens at RPI, I will work with you, but communicate with me. Don't just be late. And so I do reserve the right to be mean if you don't talk to me about it, but I'm really going to try not to be mean. Like I mentioned before, the grading is completely anonymous. Do not write your name on your assignment. Please write your RIN. And then also, if you work with other people, please write their RIN and then indicate which one is you, so I give the grade to the right person. Yeah, and working with friends is totally fine. But when the time comes to write a report, because there's going to be reports that go with your homework assignments, I would like you each to write your own report, even if you work together on the coding and that sort of thing. And if you work together on the coding, I expect you to police yourselves. If there's one person that's not pulling their weight, that's, you can talk to me about that, but, hopefully y'all have the good sense. You're all grad students by now. I don't think any of you is a lazy bones. I don't think anyone's not going to pull their weight. I sincerely hope. We'll see about that. But certainly each student is expected to write their own report. So if I get 2 identical reports, there's going to be a problem. So we'll talk about that. So homework is the bad news. Exams, hang on. There's a term project too. All right, we'll talk about the exams in a minute. Term project is going to be worth 20% of your overall course grade. And so this is going to be going on in the background throughout the semester. And I'll post some more material about this in a little bit. The term project is going to be to find a journal or a conference paper of your choosing, and I will provide a list, or you can go out and find your own, something that has to do with guidance, navigation, and control, something that interests you, hopefully. And your job is going to be to read and thoroughly digest the material. And then the big one is to be able to reproduce their results. So if they have equations, you need to understand those equations, and you need to be able to code up, if they say, we came up with some new orbit determination method, and then we decided to do a Monte Carlo analysis. And it's like, I expect you to be able to do that too, right? So pick your journal paper carefully, pick something that you can reproduce, and I'd like you to reproduce their results. Or maybe not. Maybe you'll find that you got something different. And as long as you feel as an engineer that you are, within, like, I don't think I made a mistake. Maybe they made a mistake. I don't know. Let's have that discussion. Absolutely. I've read journal papers before where I found mistakes, and that really made me feel like a PhD when I found mistakes in something that was published. So if that happens to you, that's fantastic. But your project, which would be good to start on as soon as possible. I'm going to do my best to kind of lighten the load on the homework later in the semester, because I expect that folks are going to kind of back burner this and then hopefully not do it all at the end. But if you do it all at the end, I want to try to be nice on the homework front. Read the paper, thoroughly digest the material, be able to reproduce their results. And then finally, and this is very important, I want to see your communication skills in action. I want to see you explain the paper concisely. And so we're going to schedule 20-minute presentations outside of class time, because there just aren't going to be, I don't have enough lectures to sacrifice them for everybody presents in front of the class. So we might need to have some day, maybe I take a day off of work or something like that. We'll figure it out. But there's going to be a day outside of class where we all just do 20-minute time slots, and I'll listen to your presentation and I'll give you feedback. And so that's the term project. Questions on homework or term project? Good stuff. All right, moving on. The good news is the exams. There will be no exams, period. There's absolutely no exams in this class for multiple reasons. The first thing is I've had to proctor exams remotely before when I was a TA during COVID, and it was just a bloody nightmare. It's not good. There's no way to make sure that people aren't cheating. Now, I trust all of you not to cheat, but especially when you're working with undergrads, there's no way to be sure. And so I also, in my opinion, I remember homework assignments that I did 5, 6, 7 years ago. I don't remember exams that I took towards the end of my time at RPI. This is my personal opinion. I have my own wild new agey thoughts about the way that education should work. I don't think that exams make engineers better at being engineers at all. I think that they're a necessary evil to see who's smart and who's not. But like, you're all grad students, you're all smart. So no, I'm not going to be giving anybody any exams. I also just really don't feel like writing exams. That was one of the worst experiences of grad school, is sitting down with a huge stack of exams and knowing that it's going to be 8 hours until you're through it. It's just no, we will not be doing that. So no exams. So don't worry about that. All you have to worry about is a new computational homework assignment due every other week, and those are going to be plenty. And then the term project. That's going to be it. I remember, especially early grad school, that the average homework assignment that I got, especially from like systems analysis techniques or robotics, on average, those took about 20 to 30 hours a pop. I remember being many, many late nights working on those. Your homework assignment should not take you 30 hours, but they might take 15. So, I mean, definitely take these seriously. They're going to take a little while. I timed myself. One of the homework assignments, I wanted to see how long it would take me to do it completely from scratch. And I knew what to do, and it took me, I think it was 6 hours. So it's like knowing what to do is still 6 to 8 roughly. So I would at least double that if you're learning it for the first time. So homework's going to be a doozy. Exams don't exist. I hope that those cancel each other out. There's also going to be an extra credit opportunity, which is based roughly off of the extra credit opportunity that Kurt Anderson gave in his spaceflight mechanics class. His was to teach yourself a software called STK for Systems Toolkit. Mine is going to be to teach yourself a software called Kerbal Space Program. Kerbal Space Program is one of my favorite computer games of all time. I found it in 2015 when I first joined RPI. It was actually the summer before I started RPI. And I mean, Kerbal is just a fun, quirky game where there's these little alien fellas that you can send to space, and it's just a lot of fun. But at the same time, it's actually a pretty robust physics simulator, and it really doesn't hold your hand. Like, you will develop, if you put 10 to 15 hours into Kerbal Space Program, you will develop a decent like understanding of orbital mechanics, and it will be an experiential learning thing. Like I played Kerbal Space Program, and then I took spaceflight mechanics, so that when Kurt Anderson taught me what an inclination change was, I already knew what an inclination change was. I just learned the name for it, right? Same thing with a Hohmann transfer and so on and so forth. So I have 1,000 hours in Kerbal Space Program. People at work make fun of me for playing a computer game that looks just like my job, but I'm like, oh no, no. I found a job that looks just like my computer game. So it's near and dear to my heart. If you decide that you want to play the game, I can't. I think it's like $20 on Steam. I can't remember what it costs. Hopefully, it's not too expensive. I don't want to break the bank. But it's available on Steam. If you can demonstrate that you can lob a Kerbal astronaut into orbit and then return them safely to the Earth, that will be worth 2% of your course grade. So that gets slapped directly on your course average, whatever it would have been. And then additionally, if you can demonstrate an Apollo-style moon or moon landing, it's going to be another 3%. So if you do both of those, which, the moon landing is going to be quite a bit harder than orbit, that'll be 5% added to your total course grade. So hopefully I've kind of put a carrot on a stick in front of you to make you learn Kerbal Space Program. I definitely think it's worth it. There was a kind of study that was done, and some of you might know this better than I do. Was it a year or two ago in spaceflight mechanics, where they looked at the performance of students in the class versus hours played in Kerbal Space Program, and the correlation was shocking. I mean, it's a really good idea to have had at least 10 to 20 hours in this game, and so I definitely I hope that you'll consider it. And some of you have done this already. Some of you, an Apollo-style moon landing, which when I say Apollo-style, I mean one vehicle goes to the moon, breaks in half, part of it lands, part of it stays in orbit, and then you launch the one that landed, you rendezvous them in orbit, and then you bring the crew safely back home again, the same way they did it on the Apollo missions. If you can demonstrate that to me, some of you can do that right now. That's 5% of your whole course grade. So, I mean, that's pretty much it. And so I think I'll happily accept like a series of screenshots, or I don't know, we'll figure out the best way to do the demonstration. But that is your extra credit opportunity. I hope you'll consider it. The grading breakdown. So I might have alluded to this before, but I have absolutely no problem giving everybody in this class an A, and I fully intend to give everybody in this class an A. So I don't want you to worry about your grades, right? I want this to be more like a clubhouse or some sort of, engineering firm where, I would rather you think of me as like a supervisor at your engineering job than like a teacher that has some grade thing over you. I will specifically reach out to you if you were cruising for anything other than an A, right? If it's looking like it's going to be an A- or a B, I will tell you. I really don't care. Like I'm not in the business of giving some people A's, some people B's, some people C's. This is a small enough class that I really want to coach each and every one of you to success. And so we'll see. Maybe this is like a hippy dippy new agey way of thinking about education. But this is what I'm going to try. This is my first ever semester teaching, so we'll see how it goes. If you decide to make your grade appeal, I have to put that in there. Like if you don't like your grade on a homework assignment, really what you should do is, we should chat and you should say, oh, look, I really don't think you did your best on this part, but I think you can do better here. We should keep a constant dialogue, especially if there's part of your, grade that you don't like. But I have to have something in the syllabus that says, grade appeals must be made within 1 week of receiving a graded assignment back, so on and so forth. What I don't want to do is have people at the end of the semester who've done a lousy job the entire semester try all at once to kind of get a bunch of points back. But I'm hoping that because this is a graduate level class, we won't run into that problem. Like I trust you all not to have that issue. So the way the class is going to break down, class participation is 10%. What that really means is that I reserve the right to remove up to 1 letter grade from your class average if I think that you're being rude or disruptive or just not being a good student. I don't expect anybody to get less than full marks for their class participation. There are 7 homework assignments, homework 0 through homework 6. It's Python, so it starts with 0 instead of like MATLAB where it starts at 1. You'll see why in a minute. But each of those is worth a letter grade, and then the term project is worth 20%, and then that's everything. That's 100. And then your Kerbal Space Program is worth either 2 or I guess I should say a total of 5% if you do both of them. So that's the grade breakdown. What's next? Oh yes, don't cheat. There's a statement of academic integrity in the syllabus. Don't cheat. I don't really know how you would cheat because there aren't exams. There's just homework assignments. I guess the way that you would cheat is putting in the absolute bare minimum effort on a homework assignment and making your friends do the work for you, and then kind of copying parts of their report. I really don't think we're going to see that happen. All of you are graduate students, or you will be graduate students if you're undergrads, and I really trust you not to do that. But I just feel like I should say it at least once. Like what you put out or what you put into this class is what you get out. If you put the bare minimum in, you're going to get the bare minimum out. What I'm more worried about is what I call distracted learning, right? So, and I'm guilty of this too. Like I remember taking classes remotely during COVID as a TA, because I was course complete by the time COVID started up. But and maybe having something open, on my other, maybe I was also checking my email, or I was on my phone or something like that. I have a thing in the syllabus that discusses this. I don't know if you're doing that, but I hope that you don't. I really hope that you do your best to pay attention. I'm going to do my best to keep the lectures as interesting as possible. When I started at NASA, I attended this like a orientation training that we do there, and the guest speaker was an astronaut named Reed Wiseman, who's actually an RPI graduate. So we'll talk about all the various astronauts. Those of you that aren't familiar, Reed Wiseman is going to the moon like later this year or early next year, and we will definitely have ample time to talk about the Artemis missions during this class. But Reed specifically said, like, somebody asked him what his advice is for new engineers. And he said, when you're in a meeting, don't also be checking your email. Don't also be on your phone. Don't also be doing math on a different sheet of paper. If you're in a meeting, either pay attention or leave the meeting. And he said this with an air of like, please don't make a mistake, because I'm going to space on the vehicle that you designed. And so I would say that, Reed, as an RPI alum, is somebody that you definitely don't want to upset. So I expect everybody, to the extent that you can, to attend every lecture, ask questions, engage, and work with others. And I think after that, oh yes, one more thing. But here we'll pause there. That's a natural pausing point. If anybody has any questions or you want to chat. Okay, so far so good. So I'm going to have a cold calling policy in this class, and part of this, and you might really hate me for this, and we'll see. If I get enough feedback and people say, Paul, please don't do this, then that's maybe we'll back off of it. But what I'd like to do, what I'd like to try doing, is if I reach a point where I'm in the middle of a derivation and I say, what would you do next? And then it's crickets. Or if I find myself at the front of class, like, Bueller, anybody, Bueller? It's like, I reserve the right to just cold call people and say, what do you think? And I'm going to ask you to chime in with your thoughts on a particular discussion. I want you to get over, if any of you have a fear of answering questions in class, I want you to get over that here, because no one's going to think you're dumb if you don't get it. No one's going to get mad at you if you don't get it. Even if you haven't been paying attention, it's like, just do your best. But I want to keep everybody engaged. And I know that if you know that you're not about to be called on, it's really easy to kind of check out mentally. And so I might intermittently say, just pick somebody's name and then say, hey, what do you think about this? Or what would you do next in this derivation? Or how would you find the position of this vehicle? And so you don't have to be right, but please try your best. And your answer could be, I'm sorry, professor, I don't understand. Don't call me professor, call me Paul. Sorry, Paul, I don't understand. Could you please explain it? That's fine too, but just I want to get people engaged. I was originally thinking of doing something really evil and writing like a Python script, which would be like a random name generator, and then it would pop out a name, and then that would be the person who answers the question. But I came up with something much lower tech, because there's no point in over engineering. I have on a piece of paper here in front of me a list of people. There are 16 of you, and I have a analog random number generator, which is a 20-sided die from Dungeons and Dragons. And I'm just going to roll a die and we'll see what we come up with. So just as a little, we'll see how this goes. There we go. Number 12 is Abby Rowland. Abby, you still here?
Yeah, hi.
Hi, Abby. Sorry, you were the first one. Congratulations.
Cool.
Yep. So there's going to be a bunch of that. So thanks for paying attention. I appreciate that. The other thing is, and maybe I should have mentioned this before I cold called the Abby, is we have a safety word, and that is eject. If you say the word eject, I'm not going to ask any questions. Like maybe your dog died this morning and you're having the worst day of your life and you're barely able to attend lecture, or maybe you're in your dorm, probably not a dorm if you're a grad student, but maybe you're at your apartment and you have two roommates and they're fighting, and it's going to be really awkward if you turn it on. Like I've had really rough days where I barely made it to lecture. And if you're having one of those days and then I ask you about Kalman filter derivations, you have the right to tell me no, and I won't ask questions about it. It's just like, okay, if you say eject, we're done. No questions. So we're going to test that out. 18. There's no number 18 in this class. Y'all got lucky. I got 12 again. Abby, we're not going to ask you twice. We'll try one more time. Number 15, Italia. Italia, are you here today?
Hello.
Hi, can you say eject for me?
Eject.
All right, no questions asked. We're not moving on. All right, great. Thank you very much, Italia. All right. So that's going to be the cold calling policy. If I feel a little bit lonely, I reserve the right to roll this die and then call somebody's name at random. And if you don't like it, then just say eject, and we'll move on. But I really hope that you don't. I don't want people to abuse eject if they just don't know the answer to the question. It's like, give me the wrong answer. I don't care. I want to know what you're thinking. Eject is for I really can't right now. That's really what eject means. So moving on, homework 0, which is going to be posted later today. I'll make sure that this goes up before midnight tonight. Homework 0 is going to be due in 2 weeks, and it is weighted the same as some of the homework assignments that will take you 10 to 15 to 20 hours. Homework 0 should not take you 10 to 15 to 20 hours. Homework 0 is I want your resume, your cover letter, and a headshot, or some sort of photo of you that you think looks professional. These are things that I hope you have on hand and are ready to go, which would mean that you just get full marks. I mean, we're going to be clear. Everybody is going to get full credit for this homework assignment. I will badger you if you don't send me your resume, your cover letter, and your headshot. But I want to specifically have kind of we're going to have fun with it, basically. I came up with a fake company, which does not exist, called the RPI Instrumentation Laboratory. This says that it's already posted on LMS, but it is not. It's going to be due on January 19th, so you have plenty of time to work on this. But I want you to read the job listing. And actually, I'm going to tab out from the PowerPoint presentation briefly and click over to here. Don't look at that. Here's the syllabus. This is going to be posted soon. This is the job listing. So we're just going to read the first part. In this assignment, you will be responding to a fictitious job posting. Your deliverables will be a resume, cover letter, and professional-looking photo of yourself. If you already have these on hand, this will be an extremely short homework assignment. This is designed to help me get to know you better and also to make sure that your job application skills are sharp. So I hope that all of you are familiar with resumes and cover letters. If you're not, you can look up some stuff online. You can see how it's done. What is it? The CCPD, the Center for Career and Professional Development at RPI, is very good about helping people. So now is the time to make sure that you are sharp about your job application skills, because you will certainly need them. But so the job listing is as follows. The RPI Instrumentation Laboratory, which is a play on the MIT Instrumentation Laboratory, which is the company that designed the Apollo guidance computer. The RPI Instrumentation Laboratory is an almost legitimate company founded with the purpose of providing navigation, consultation, and support of human and robotic spaceflight. We are engineers, computer scientists, data reducers, and analysts dedicated to determining the position, velocity, and attitude of any vehicle whose owner can afford our services. Our customers include NASA, SpaceX, Starfleet, the Galactic Empire, the Rebel Alliance. We maintain a strict policy of neutrality in regards to stellar conflicts, and Star Command. And so the job listing goes on. I tried to be a little bit silly about it. But so read this. I want your resume. I want a specific cover letter, because those are meant to be specific to a job application, and some sort of a photo of you. And I'll post this assignment on LMS, and you've got 2 weeks to do it. And so the other homework assignments are going to be a little bit spicier. Actually, do we have time to talk about the other homework assignments? Yes, we do, actually, because the very next thing we're going to do is a 10-minute break. So really quickly, and from a bird's eye view, what I'm going to try to do is post all of the homework assignments now. So they're all done. I've been working pretty hard to try to get all the homework assignments done before the first class. And here's why. These homework assignments, and I'm going to tab through them in a minute. Wish Edge would go away. Yeah, okay, that's fine. These homework assignments are everything you have to do this semester. And I'm hoping that if you read these, some of them are going to be, oh, I think I know how to do that. And some of these are going to be, I have no clue. But I hope that will kind of inspire you to pay more attention in lecture and say, oh, this is the lecture that we start talking about inertial navigation. I'm going to need that. Or this is the lecture that, oh, Paul's going to be talking about triangulation today. We need that for homework, whatever, that sort of thing. So roughly speaking, the homework 1 is I'm going to ask you to demonstrate that you can propagate an orbit. If I give you an initial state, I want you to be able to give me its final state using 3 different methods. One of those is what are called SPICE kernels. If you're familiar with SPICE, it is a ephemeris database that's used by JPL. It's relatively straightforward to get SPICE working in MATLAB or Python or whatever else you'd like to do. I should mention, by the way, you are not expected to use any particular software like MATLAB or Python or whatever. Use whatever you like. But I personally use MATLAB. And so if you are stuck and you need help and you don't do MATLAB, I'm afraid I really can't help you. I guess I can help you from an algorithmic standpoint, but I can't help you debug if, say, you choose to do this in C or C++ or Python. But my instructions are for MATLAB. So the instructions here are how to get SPICE working in MATLAB. You also should be able to propagate the orbit of a spacecraft using ODE 45 or what is it? ODE fun. I forget what it's called in Python. ODE int, I think is what it's called in Python, for an ordinary differential equation solver. And then also just solving Kepler's equation iteratively. And if you're done and you finish this early and you're feeling happy about it, you can actually go through and demonstrate the methods of orbit determination we're going to talk about in this class. So could you go through, find the position of the spacecraft at 3 different times, and then show me Gibbs' method of orbit determination, so on and so forth. And so this is going to be a bit spicy, if you'll excuse the pun. Homework number 2 is on estimation theory. So there's a rover on the moon driving towards a beacon. It's going to be receiving and sending signals. And I'd like you to do a batch estimation of its velocity over time. I think, is it just its velocity or its position? I think it's just its velocity. And then I also talk about using a least squares and then maximum likelihood estimation to find the position and velocity of a spacecraft using beacons on the surface of the moon. That is estimation theory homework 2. Homework 3 is trilateration and triangulation. So there's a GPS problem where you have different ranges from GPS satellites and you need to find the location of a observer on the surface of the Earth. And then there's a deep space network problem. Or sorry, not deep space network. There's a method of navigating with respect to craters on the surface of the moon. So I give you the latitude and longitude of different craters and then also line of sight directions from a spacecraft. And you're meant to triangulate its position and then ultimately do orbit determination. So the later homework assignments build on the earlier homework assignments. And so the math that you do in homework 1 on orbit determination is going to help in homework 3. And the math that you do on coordinate, frame transformations is going to help later, and so on and so forth. Homework 4 is I'm going to post a image of stars. And actually, I've gotten explicit permission from NASA to post a photo that was taken by a camera on Artemis 1. Like, this is a real flight data. I can disseminate it to y'all. Y'all are allowed to see that. And you're going to write your own star tracker completely from scratch and answer me which star is which in the image and what is the attitude of the camera with respect to the inertial International Celestial Reference Frame. So homework 4 is going to be the big kahuna. This one's going to be pretty rough because you're going to do it all completely from scratch. This one took me 6 to 8 hours and I knew exactly what to do. So definitely get out in front of this one and make sure that you try to start it early. Then we have homework 5, which is Kalman filtering. So this is going to be range, rate, and bearing, or R3B measurements from the Goldstone, California Deep Space Network ground station of an Artemis spacecraft as it coasts out into deep space. And you're going to be doing sequential estimation, so coding up your own extended Kalman filter, essentially, based on the data that I give you. And then finally, homework 6, which is going to be one of the shorter ones, is horizon-based optical navigation. This is an image of Pluto. Tell me, based on this image, where the spacecraft is. That's the homework assignment. And so that's pretty much it. Those are all of the homework assignments. My hope is that you are some mixture of thinking that this sounds really cool and thinking that this sounds really intimidating. Not because I like it when you're scared, but because the more that the homework assignments seem a little bit spooky, I think the more engaged people will be in lecture. That's the hope. So I'm going to endeavor to post all of these as soon as possible so that you can read over them. They are due every other week. As a matter of fact, we've got a schedule here at the end of the syllabus. And so what we can see here is this is today, and then we've got reference frames and epochs and all that. Homework 0 is due 1/19, and then every other week we've got another homework assignment due. Also, I specifically planned this around you not having homework over spring break, so you're welcome. I think it's cruel and unusual to give homework over spring break, so I want you to enjoy your spring break to the extent that you can. Or just get caught up in other research, which is probably what's going to be probably how it's going to go if you're in grad school. But anyway, so that's my plan for the semester. Those are the homework assignments. We've got a 10-minute break coming up, and then we've got a kind of a little exercise that we're going to work through. So if you want to ask questions, you absolutely can. Otherwise, it's 6:67 for you, 5:57 for me. So we'll come back in 10 minutes. So was that 7:07 p.m. and we will resume. But I'm going to stick around and just answer questions if you have any.
The cover letter thing. Do you want us to take our name off of our resume? Or...
Yeah, so I realized that you should have your name on your resume. Yeah, so that's
okay.
I made that policy, and then I realized how dumb it sounded immediately. So for all of the other homework assignments where I'd like you to write a report and say, on January whatever, we received these signals from the Deep Space Network, and we were able to triangulate our position. That's all anonymous. I want you just to write your RIM. But for homework 0 only, I want your regular old resume, regular old cover letter, regular headshot. I mean, it's kind of tough for the headshot to be anonymous, right? Also, don't you have another? Oh yeah, you have to sign off in 2 minutes, don't you? I was going to say you should be attending your other class.
Yeah, I gotta go now.
Who starts at what is it? 8 p.m. or 7 p.m.?
It's like the class didn't have like an actual time, and then he just said, "Yeah, we're gonna do it at 7." And I was like, "Okay."
I'm sorry that happened to you. I'm going to
Well,
try
it's
to
only,
not be like
there's only 4 like synchronous sessions, which is
Oh, is this
weird, but
engineering mathematics?
yes.
Oh, I have that too.
Oh,
I
fun.
didn't know if
Yeah,
you had
it's
to leave early or go late.
I
Mm.
was just gonna leave this early.
Yeah, sure.
But,
And
yeah.
if it's more boring over there and you'd rather be over here talking about space, then I mean, no one's going to fault you, right? But I get it. You've got you got to do what you got to do. But yeah, no, sounds good to me.
Hmm. I wonder if I should just go to that one for like 5 minutes, then finish this class, and then go back to the other one because I want to stay here.
Oh, thank you. That's I appreciate that. That's good. We're going to be doing a space exercise in a minute, so if you want to, do that for a little bit and then come back here, we're going to start up at 7:07. So yeah, take all the time you need.
Okay, I'll go to that one and see if he's gonna post a video and then come back.
Sounds good.
Bye.
And I just wanted to mention my standard plug whenever people mention CVs or cover letters or resumes, that Ask a Manager is a great reference. I listed it in the chat, but
Oh, good.
seriously,
Thank you.
I love
Appreciate you.
Ask a Manager.
Yeah, that's excellent. I hope that helps people. Yeah, my hope is that most folks will already have a resume like ready to go. But if you don't, then like this is the kick in the pants that you need because like you ought to get a resume together. And yeah, it's a good habit to get into. So yeah, what is it called? Ask a manager.
Yeah, Ask a
Okay.
Manager. Her name is Allison Green. She's fantastic.
Okay.
And her workplace advice makes you feel better about any workplace you're at.
Oh, I love that. All right, sounds good. Thank you. All right, figure we'll start back up in a minute here. If I don't know if y'all can hear it outside, but it's a lightning storm going on right now in Houston, so I hope that doesn't kind of interfere with things. If it knocks my power out, that would be a bummer. So that's what that is, if that's a problem. Um, I understand that it snowed in upstate New York recently. It is in the 70s here. It's in the low 70s in Houston, so, so we just don't get a winter. Uh, anyway, so we'll start back up in a minute. Does somebody want to just chime in and let me know that I'm not speaking into the abyss? Otherwise, I'm going to roll the die again.
I hear you.
Okay, we got you. All right, appreciate you. Okay, so also wanted to highlight before we move on, my email address has changed. I feel like those of you that know me already are used to mckeep@rpi.edu. You might even try my webex.com/meet/mckeep. There is now a 2 in my email address and in my account. So when you graduate, they delete and purge your account from the system very quickly. And then if you come back as faculty, which a lot of people do. So for example, Dr. Hurst in the main department used to be a student here. I think Dr. Hicken might have used to be a student here. There's a handful of people that used to be a student here. They all have a 2 or a higher number, right? Because they deleted mckeep@rpi.edu. That does not exist anymore. And now mckeep 2. So just wanted to highlight that. If you try to reach out to me via mckeep, you will not hear back. And I would say just text me, but then it's like, no, that's we already said that. That's against the rules. So try to stick to the email if you can. It says this in the syllabus, but I'm somebody who runs on autopilot most of the time. So just a reminder about the mckeep 2. Okay, so we're going to resume presentation. And so here is a question for everybody. What is space? We're going to talk about this for the next half hour. What is space? Anybody? I'm not gonna. I might cold call people, but we'll just see who's feeling brave and wants to say what they think space is.
The sort of vacuum around all of the planets in the solar system and everything else in the expansive
All right,
universe.
that's pretty good. I could, if I wanted to be really, I could just be like, well, is space really a vacuum? I mean, there's some particles, but no, that's a pretty solid answer. Are you in space if you're on Mars, or is that like a different planet and then space surrounds Mars too? Is that what you're implying, or?
I guess that's what I was implying with my answer, but not really what
So
I meant.
this is a trick question, right? You're not. This is meant to be unanswerable. So I appreciate you for being brave. The point that I'm trying to make with this question, and this is a philosophy of mine that I learned in grad school that I think that y'all could benefit from, is that if you learn how to ask the right type of question, you are 90% of the way to your answer already. And your question needs to be well posed. So what is space is a poorly posed question. It's like, well, how do you even know that I meant outer space? I could have just meant space as in like the space bar on your keyboard. This is a very poorly posed question. There's not enough requirements on it, right? So what I'm going to propose is that if we work together and try to sharpen the definition, sharpen this question, we will answer it almost just by asking it the right way. Almost. That's what we're going to try to do. So who wants to just, if you're feeling brave, tie in with the microphone. What's a better question than what is space? What's a more answerable question? That's related, of course. No, people are feeling shy. That's all right. We'll try one more time. How about I'll ask it this way. I'll kind of lead you in the right direction. How do you know when you're in space versus when you're not in space? That's a better question. Anybody want to hazard a guess at that one? How do you know when you're in space versus when you're not in space?
Where the atmosphere ends.
Okay, solid answer. Solid answer. So let me answer your question with another answer, or I guess answer your answer with another question. When does the atmosphere end? Somebody else, because I can tell that you're brave. Somebody else. When does the atmosphere stop? Is that at a certain altitude or what?
You probably just define a density where you start to neglect it.
Ah, okay, very good. Because you might be familiar, the atmosphere doesn't just stop. There's like an exponential decay in atmospheric density as a function of height, or at least that's how we model it. Even the International Space Station, which is I think 400 or 500 kilometers in its orbit radius, has to contend with atmospheric drag. Like the giant solar panels on the ISS act like a sail, which slows it down, and they need to maneuver every once in a while to kind of maintain its orbit. So space, it doesn't just start, but engineers don't like that. Engineers like something when it just starts. You know, we like there to be a line. What's the border? Where's the edge between the atmosphere and outer space? So you see how already this is a much better question. At what point, at what altitude are you in space? And we know that that has something to do with the atmosphere. That's a better question. Okay. Anybody feeling brave? Some of you might know the answer to the question because this is an answered question. This is not a made up thing that I did. Anybody want to hazard a guess? At what altitude can you be said to be in space?
It's like 100 kilometers, right?
Correct.
Commonly.
Now, why is that the right answer? Uh-oh.
That's what the scientists decided.
That's what the scientists is. Well, we're the scientists. We're trying to figure
No,
that
we're
out for ourselves.
engineers. I don't know.
Oh, well, all right. But, you know, say you get the point that I'm going for. So it is 100 kilometers. That is the answer. Another one of my philosophies is that knowing the right answer and not knowing why is the same thing as not knowing the right answer. But I'm not trying to pick on you. That was good. 100 kilometers is correct. So here's what we're going to do. We're going to switch over to OneNote, and I'm going to start throwing some equations at you here. So we'll see how well this goes. So let's see. Here is the Earth. There you go. It's a sweet Earth, you might say. And let's say that there is some altitude above the surface of the Earth, and just pretend that this goes all the way around. And we're going to call that altitude little h. And then we're going to call this, I mean, if this is the Earth, then this would be the radius of the Earth. Does anybody have that number memorized? What is the radius of the Earth? That's a super dorky thing to have memorized, so I'm not going to fault anybody. Say again?
6.4 into 10 raised to 6.
Yes. So the number I have memorized is 6378 kilometers. You have 6.4 times 10 to the 6 meters. I'm going to say same thing. So full credit. Yes. This is just how I have it memorized. But you could use 6.4 times. Absolutely. So that's the radius of the Earth. The question is, at what altitude h are we in space? And the answer is 100 kilometers. And then the question is why. Okay. So there was a fellow long time ago, he was born in 1881, lived until 1963, named Theodore von Karman. The phrase von Karman might sound a little bit familiar because the border between Earth and space is called the von Karman line. So that's kind of where we're going with this. Which, interestingly enough, he had a graduate student. Named Richard Gilman Folsom. Who can tell me why that name is important? Who was Richard Gilman Folsom? Oh, come on. One of you has seen that name.
Library has this.
Yeah, that's the library. Exactly. He's the former RPI president, Richard Gilman Folsom. It was one of Theodore von Karman's graduate students, which I just thought was a neat side, but that doesn't really matter. But yeah, that very 70s looking library that we have is the Richard Gilman Folsom Library, and he was one of Theodore von Karman's students. That's a tangent. Okay. So what von Karman said, he was working in the 1940s when we actually started getting serious about higher and higher altitude flight. And he really thought through this question, at what h are we in space? And so what he came up with was this. This was his answer. Here is an airplane. Bear with me. So it's got a nose. It's got a wing. Oh boy. This is going to be a rough semester if this is how Paul's airplanes work, right? And we know that as your altitude increases, your velocity has to increase to maintain the same lift, right? By the way, lift. Does anybody remember the equation for the force of lift? Oh, this is like fundamentals of flight, undergrad level stuff. Anybody remember?
Half rho v square CDS.
1/2 rho v squared. We're going to say CL.
CL, my bad.
And what was the last one? S?
Wingspan.
So we're going to, yeah, so this is a little bit different.
Yeah.
The version I'm familiar with has density, velocity, coefficient of lift, and the projected frontal area. So like if you look at an aircraft from the front, it's like that area. And then maybe it's got a, you know, there's your cross section. So that's your area A. Anyway, very good. So that is the force of lift. Okay, so we're getting somewhere. So the thing is, what you'll notice, the force of lift does not exist explicitly in this equation, but there is this term rho. And do we know rho as a function of h? I mean, you can actually look that up in a table. I'm going to use a specific atmospheric density model, which we used in spaceflight mechanics. So if any of you, if I was your TA for spaceflight mechanics, the Howard Curtis book, example 11.3, used rho is equal to some initial rho times the exponential function, which is the same thing as e to the power of, I just like to write this better, negative altitude over reference altitude, where rho naught, well, we'll get to the numbers later. That's fine. Here is atmospheric density as a function of altitude from Howard Curtis. So this is Howard Curtis 11.3. Okay, I promise we're building towards something. Bear with me for a little bit. So we know that the force of lift has, you know, velocity and projected frontal area and coefficient of lift and rho. And we also know, which this should make sense, that atmospheric density drops off exponentially with altitude, and it's a negative exponent. So it drops off exponentially with altitude. So then, okay, how does that help us? What this means is to maintain the same lift, to stay in level flight at a higher and higher and higher altitude will require a much, much faster velocity. And what you'll find is that the velocity required to maintain level flight as a function of atmosphere is actually, it's like an exponent squared. It's like a crazy steep line, basically. And so wouldn't there reach a point where you're going so fast that you just might as well be in orbit anyway? And that's what Richard Gilman Folsom, I'm sorry, not Richard Gilman, that's what Theodore von Karman asked, right? So at some velocity, at some altitude, velocity is so high that you are basically in orbit. And so Theodore von Karman said, we can derive the altitude at which the velocity is so high that you might as well just be in orbit. And at that point, you can just take the wings off the vehicle, right? Like if you're designing a space plane, its wings are now useless. It is in orbit. As a matter of fact, the wings would be causing drag. And so at that altitude, you were in space. And as it turns out, the answer is 100 kilometers, which is a really nice round number, actually. It's not exactly 100 kilometers. We'll see what it is in a minute. But do you see how we started with what is space, and then we got to what is the edge of space, and then we defined it even better. We said, at what altitude is your velocity so high that you might as well be at an orbital velocity? And that is such a better defined question that we have almost answered it already. And that's basically what we're going to do. So hopefully that makes sense. So let's do some free body diagram, shall we? So I'm going to do my very best X15. So bear with me for a little bit here. It's got like a little, ooh, okay, off to a rough start. Free body diagram. It's got like a pointy nose and then like that. And then it's got like that. And then here, and maybe it's got an engine coming off the back. And it's got little stubby wings. And then that goes like that. And then someone's having a good time. And this part says NASA. And this is an X-15 space plane, which I believe is the first plane that's been to space and one of the only planes that's been to space. We're going to be looking at X-15. So maybe it has another wing on the opposite side. Okay, there you go. You can tell that I'm not an artist, but this is the best I could do for an X-15 space plane. And what we're going to say is that in the case of a two-body orbit, we're going to do this at the high school math level, basically. A two-body orbit, we can say essentially that the centripetal force, which is caused by the fact that you're swinging around at a very high velocity, is equal to the force of gravity, right? That's really what orbit means, is that the force of the Earth on you due to gravity is, or counteracts the centrifugal force, essentially, that's keeping you in orbit. And this is going to be a really hand-wavy derivation. We're going to get into some snazzier math later, but just bear with me. We're going to keep this at the late high school, early undergrad level for now. So this, you might remember, for a body moving in a circular arc is mv squared over r. And this is equal to, remember Newton, what is it? The gravitational constant times the mass of the first body times the mass of the second body over the orbital radius squared, right? And so if you take a look at this, cancel, 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 what we get is that your orbital velocity, v orbit, is the square root of your gravitational parameter times the mass of the Earth over your orbit radius. Or some people will see this as the square root of mu over r, where we define mu, the Greek letter mu, to be the gravitational parameter times the mass of the Earth, essentially. Okay, great. This should look a little bit familiar, right? So your v orbit is square root of mu over r. Now, what about for what I'm going to call space flight? In the case of space flight, you've got your centrifugal force. You've got the natural tendency of the spacecraft to fly off because it's going in a very high velocity arc around the Earth that's going up. You've got the force of lift as well, and you've got that counteracting force due to gravity. So your equation now is going to look like mv squared over r plus 1/2 rho, what is it? Projected frontal area, coefficient of lift, v squared, is equal to g capital M little m over r, right? So this is our equation for space flight. And actually, we're going to tidy this up in a little bit. First of all, we said that gm is equal to mu. I'm also going to define r, which is the radius from the center of the Earth to where you are, is defined such that it's equal to the radius of the Earth plus your altitude. So I'm going to replace that. And I'm also going to pop in our equation for our atmospheric density. And so what we get is your mass of your vehicle times the velocity squared over the radius of the Earth plus h plus 1/2 rho naught exponential function of negative altitude over altitude naught. Projected frontal area, coefficient of lift, velocity squared is equal to mu mass of your vehicle over radius of the Earth plus h. Oh, I'm sorry, squared. Something felt wrong there. Okay, mu m over h. Okay, so what else do we need to know? Well, from the Howard Curtis textbook, our reference atmospheric density is 1.225 kilograms per meter cubed, and our reference altitude is 7.5 kilometers. Be careful of units. Now we need what? We need mu. You might have that memorized as 398,600 kilometers cubed per second squared, I believe, are the units on that. Correct me if I'm wrong. We know the radius of the Earth from before. Okay, what about mass, projected frontal area, and coefficient of lift? Where do we get those from? Because those seem like they would be specific to a vehicle, wouldn't they? Anybody have any thoughts on that? Oh, y'all are going to make me get the 20-sided die out. Don't do that to me. Any wild guess on where we might get a mass, a projected frontal area, and a coefficient of lift? Oh, you guys are doing it to me. All right, let's see who's unlucky today. We'll see who's. We got number 6, Alex Jin. Alex, are you here with us today? Ooh, that's a lucky one. All right, we'll try one more, and then I'll just give you an answer. If 2 people get unlucky and they can't make it, then that's fine. Let's see here. Number 13 is Justin Smith. Justin, are you in lecture today?
Yes, I am.
Oh, Justin, you got unlucky, bud. I'm sorry about that. You got to tell me. Hopefully you've been following things. Does this make sense so far? Do you have any questions on where we are? Is this mostly okay?
Yeah, it makes sense.
All right. So now I'm asking you, we need a mass, a vehicle projected frontal area, and a coefficient of lift to plug into this equation. Where do we get those? Like what do we what do we do here? Any thoughts? I don't know is a valid answer, but I want to hear what you think.
Well, I don't have anything profound to say, but
Okay.
I know that we have the rocket equation, and if
Okay.
the Earth was a little bit bigger, we wouldn't have the material science necessary to build a rocket that could achieve the delta V to escape the gravitational pull of the Earth. So I imagine we could apply that concept to this in a similar way.
So that is absolutely correct. Completely unrelated. So no, I'm sorry. That's not what I'm looking for. But I give you a lot of credit for knowing that. That's a pretty impressive fact.
All right, I'll take it.
That's all right. All right. So I picked on you, and there's no shame in not having the exact answer off the top of your head. I hope that we can get past that. But I appreciate you taking a swing at it. It's very, very good, Justin. And I'm glad to have you here, by the way. I remember you were a fun student to work with back in ModCon. Anyway, so here's the answer that I was looking for is just go look it up. So I just went and found some papers and I went and looked up, and this was fun because I have access to NASA internal documents, and I think it's okay to share this information. It's probably fine. But in case you're wondering, the X-15 has a dry mass of 6577 kilograms, as a projected frontal area of 3.168 meters squared. And they did some wind tunnel testing, and they found that as the Mach number goes to infinity, the coefficient of lift approaches 0.2. So we're going to treat it that way. And now you might be saying, well, Paul, aren't we now answering this question for a specific vehicle? And the answer is yes, actually. The answer to at what altitude might you just be in orbit anyway is actually a vehicle specific answer. And so we basically just need to plug in some numbers. When Theodore von Karman was doing his math, the X-15 had not been designed yet. He did his math based on the Bell X-2, which is one of the predecessors of the X-15. But yeah, so we're going to plug in these numbers. And so what I would propose is that you can solve this equation for find V flight as a function of h. Okay, so if you take this equation, you have all these numbers, you plug it in, you find the velocity of your flight as a function of h, and we also know that the velocity of our orbit, the orbit, if there were no wings on the body at all, is the square root of mu over re plus h. What I would propose is that we could then take a look at those two curves, and much like a cooking show, where it's like, oh, we actually already put a cake in the oven before the thing started. I already did this in MATLAB, and so I'm going to post these notes a little bit later, but I did this in MATLAB, and you're encouraged to do it yourself. Here's the results. So the X-15 spaceplane uses these parameters. Howard Curtis's atmospheric density model uses these parameters. The velocity of an orbiting vehicle, which you would expect is a negative linear relationship. Velocity goes down as altitude increases. And the velocity of space flight looks like it's all set to be this kind of exponential curve, but it actually kind of peters out because you reach this point where you're going so fast that you don't need that much lift to help you. And by the time, I mean, I would argue that these two lines converge at 100 kilometers. You could argue that they converge at 80 kilometers. You could argue that they converge at 120 kilometers. The US military uses 50 miles as the altitude of space, which I believe is 86 kilometers, but I don't know metric unit conversions. So it's really anybody's guess. But Theodore von Karman thought, gosh, it looks really pretty if it was 100 kilometers. So that is a completely, I mean, not completely made up. It's based on some engineering. But the idea that space is 100 kilometers up is, kind of an academic armchair exercise. Doesn't really have that much bearing on things. But engineers like to have numbers to assign to things. And so the main takeaway from this is not so much that's what the edge of space is. The main thing I want you to take away is that as a graduate student, as a researcher, as an engineer, learning to ask questions the right way is the hard part, and math is the easy part. That's my main point. Anyway, with that said, if anybody has any questions, I'm going to stick around to answer all of them. Otherwise, class is dismissed. Thank you so much for coming to the first lecture of Introduction to Spacecraft Navigation. We'll meet back here at the same time on Thursday, and we'll start talking about reference systems and reference frames. And yeah, thank you for coming.
Thank you.
You're very welcome. I'm also going to stop the recording now here.